I built this robot that can balance a ball, and this video is about how I made it. When analyzing the process of balancing a ball on a platform, we can break the procedure into 3 steps: to locate, compute, and actuate. Imagine you're trying to do this by hand. First, you need to know where the ball is. Then, considering how far it is away from the center and how fast it's moving, you will adjust the plate accordingly. That is, you will tilt the plate more aggressively if it's farther away from the center, and gently if it's closer. For the robot, the process is very similar, but an algorithm tracks the ball's position and a control loop determines how much adjustment is needed. The robot's body, the platform where the ball rests on, must have at least 2 degrees of freedom so that it can guide the ball to any 2-dimensional direction. A straightforward approach is to use a motorized gimbal platform with 2 motors, one for each axis. For this project, I went further and used a 3 degrees of freedom system, a free RRS parallel manipulator, which is capable of moving up and down as well. The name suggests that there are 3 separate arms that control the platform together. Each arm has a RRS configuration. The R stands for rotational joint and the S stands for spherical joint. They need to be connected by 2 links like this. With 3 arms, you can tilt the platform in any directions. So the rest of the design is just to put the motors together and house the electronics. I used 3 RC servo motors as the actuators because they're cheap. Then the Raspberry Pi is used as a main controller, and because it doesn't have any internal PWM clock, I added a PCA 9685 driver to run the servos. There's also a Raspberry Pi V2 camera that tracks the ball, which can run at around 30 FPS in action. Now that we're done with the design, let's put everything together. And this is how it looks fully assembled. You can see how the 3 arms work together to tilt the platform. Now let's begin on the software, how to control the robot. And the answer is we need to use inverse kinematics. Inverse kinematics is a very important engineering concept that allows us to trace back joint movement based on the end effect. The inverse kinematics solution for a free RRS parallel manipulator is fortunately quite simple. All you have to do is treat each joint as a point in its 3D space and apply some basic geometry and trigonometry. I wrote a simple GUI using Qt to test the inverse kinematics here. And as you can see, we can project a desired orientation onto motor actuation. Like I already said, the camera captures the position of the ball. And what's really happening is that there are many image processing masks are layered to filter the ball from its background. I mainly use the color filter and the shape filter built with basic OpenCV functions to do this. And here's the result. Next is the most important part of the software, teaching the machine exactly how to adjust the plate. I used the PID controller to achieve this. It's the simplest yet extremely powerful feedback controller and suited this project perfectly. Essentially, we want to keep the ball near the center so that it's really hard for it to fall off. Therefore, the distance of the ball from the center is treated as an error. The proportional term is directly linked to the error. The larger the error, the stronger the correction. The derivative term reacts to how quickly the error is changing. So if the ball is moving fast, it applies a counteractive force to slow it down. The integral term deals with any persistent error that accumulates over time, correcting any steady-state drift. By combining these terms, it produces an effective correction that addresses the current state of the system. Then each coefficient, or gain, which are the Kp, Ki, and Kd, has to be precisely tuned to achieve optimal performance. This is also the most painful part of the entire project. In our system, we run 2 separate PID loops, one for the x-axis and one for the y-axis, so that we can manipulate the ball's trajectory in both directions. Adding up the 2 vectors, we get both the direction and magnitude of the correction, which is then projected to become the normal vector of the plane. And the formula for the transformation is illustrated here. So, with all these tools built, we can start tuning the PID. MATLAB Simulink is a great tool for building simulation and virtual testing, so I built a simulation for this robot by modeling the trajectory of the ball. If you have the advanced version, you can even use the Auto PID Tune feature, which certainly helps with the actual tuning process. After many hours of trying, it finally converged to a usable level. That concludes my journey in building this ball balancing robot. I hope you enjoy it. I will open source all of the design files and code on my GitHub. You can also find a more detailed explanation of the inverse kinematics and computer vision part of the project on my blog. All of the links will be available in the description. See you at my next project.